We're going to be starting off our Analog 2 session. We have about 5 more talks here, and then we're going to take it into discussion, Q&A session, and then hopefully take all this information back into our breakouts later today. And so we're going to start off with a talk from Pascal Lee about lessons learned from the Haughton-Mars project and the Devon Island Arctic and a Mars forward strategy.
Good morning, or good afternoon, everybody. My background is not in the Arctic, but I'm going to be talking about our work on Devon at the Haughton-Mars project, and also continue thinking in the direction of where the Artemis program should prepare us for.
Hey, Pascal, might be better off to turn off your video to preserve the bandwidth here, if you can still hear me. Are you still there?
Yes, I'm there. Do you hear me?
Yes, we can. Yes.
Next slide, please. Not sure what happened there. So this is a plot that you will see a few more times in this talk. It shows on the x-axis the log of the two-way communications time to the destination, and on the y-axis, the autonomy from Earth, which is a sort of a qualitative assessment of the level of autonomy from 0 to 100%, but specifically for tactical decision-making purposes. So the Apollo missions were sortie missions. They were short duration, short roaming range by design and budget. The comms two-way light travel time was 3 light seconds. The science op support was heavily reliant on a science backroom, providing guidance and oversight, and of course strategic planning ahead of all this. And the tactical autonomy ranged from relatively low to slightly less low by the end of the Apollo program. And this is not to minimize the autonomy and the PI ship that Jack Schmitt had on the moon on Apollo 17, but just to remain a very constrained type of a way of doing field work. Next slide. Where we want to go down the road is Mars, and for that we will hopefully start with a fixed-based mode of operation as opposed to sortie mission, where we would contemplate a long duration stay on the surface, but also from the standpoint of using that base, and where we would roam over distances that would, of course, be increasingly large, expanding our exploration zone. The two-way comms time ramps up to between 7 and 44 light minutes. Science op support will still have the benefit, of course, of strategic planning from the Earth, but it will be severely time delayed. So tactical input would be difficult, although once you have a fixed base, you have the ability to return to sites, to regions of interest, to targets of interest, and then you can iterate in that way with the input from the science support team on the Earth. The crew tactical autonomy will have to be high to possibly up to 100% far down the road. Next slide. So there's an autonomy leap. We have to somehow use the Artemis program to bridge this gap between the end of our experience with the Apollo program and how we hope to be set up and prepared for the initial Mars surface missions starting from a fixed base. Next slide. So I'm going to talk to you about our experience on Devon Island. Devon is the largest uninhabited island on Earth. It's in the high Arctic. It's the largest continuous expanse of rocky polar desert on Earth. It's the home of Houghton crater, Houghton impact structure, 20 kilometers in diameter. The age is 23 million years old, thanks to Kelsey Young. And it's the home of the NASA Haughton-Mars project, which has been going on for almost a quarter century now. Next slide. So we, of course, focus on analog studies in relation to Mars, but also the moon. On the left, I'm showing you 2 columns, one of which is Mars features, the other is Devon features. They are at least morphologic analogs, but possibly genetic ones as well. So the important things to note is that this is a fixed-based type of exploration mode and scenario, and also it's a vehicle-based exploration mode of work. So rather than doing a lot of our field work strictly by hikes on foot from our base camp, we head out on vehicles. There's a lot of drive-by geology. There's a lot of flexibility afforded by a range of types of vehicles that we use, from all-terrain ATVs to sort of pressurized rover simulators in the form of Humvees. Next slide. So I'll focus on the second paragraph here. First of all, we do real field science, not a simulation thereof. That's an important driver of our lessons learned. The science, of course, is relevant, not just from a content standpoint, but from an ops standpoint for Mars and the Moon. It's outpost-based. I've mentioned this before. It's very important because the way you do field science, for example, out of Antarctic bases, is quite different from how you would do it if you were somehow doing a sortie to Antarctica, which, of course, some of the remote field teams do as well. It's a vehicle-based approach, and the important thing is that it's heavily safety constrained. We're in an extreme environment. We incidentally, on our project, have had no accidents in 25, well, no serious injury in over 10,000 person days of operations. But the point is, our activities are severely constrained by safety concerns. Next slide. So it's a decent moon analog, or at least it's a relevant moon analog as well. Here's Haughton Crater compared to Shackleton. Impact structure, 20 kilometers or so in class size. There's impact rubble all around, permafrost with ground ice. There's, in the summer at Haughton, permanent solar power available. Comms are horizontal. At Haughton Crater, you have to look at the horizon to see geostationary satellites, so you have all kinds of ground effects that are quite relevant to direct-to-Earth comms from Shackleton, for example. And of course, it's outpost-based as well. Next slide. So this is just some nice pictures. Maybe if you have black and white glasses, you will see Haughton has terrain that looks eerily like the moon in many ways. And what's important here, it's not necessarily the specific content of the geology. The rocks, for example, on the moon are basaltic here. At Haughton, there are limestones and dolomites, but the topography, the scale of exploration is what's relevant here, and this is a very important thing to note. So, as much as I do agree that Arizona would be an ideal location to do the core training of the crews and a lot of the sort of specific tasking learning, at the same time, it would be very important to include sites like this that have the scale of the exploration that we plan to do on the Moon and Mars as part of the portfolio. Next slide. So the ops model of work at Haughton is PI-defined research. There's a lot of pre-deployment planning, but also in-situ replanning and iterations. The science ops tactics is that the field crews are relatively autonomous. There's sometimes a guided traverse lead guiding the traverse if the PI is not experienced. The operations are tracked in situ. We've had a number of ops studies over the years. I'll leave you to look at these in more detail on your own time. Next slide. Next slide. Yep. So how do you segue from the Apollo experience using Artemis to get ready for Mars? Well, hopefully we will evolve on purpose, from crews having relatively low autonomy to more autonomy. We might want to test time-delayed operations, actually quite systematically, and then also maybe insert the support of artificial intelligence, which might come in handy when it comes time to doing Mars missions for real-time support for the crew, while the science support team on the Earth will have to iterate over several excursions. Next slide. So how do you bridge this autonomy leap, this autonomy gap? Next slide. Well, the Artemis program hopefully will pick up where Apollo 17 left things, with sortie missions, heavily reliant on the support of the science support team back on Earth in real time, but that progressively we will segue to a mode where we allow the crews on the Moon to have essentially the autonomy that initial Mars crews would have. And I think this is a very important step to include in our planning for Artemis, which is to not necessarily settle on any single particular mode of operational support, but to understand that we will want to start with one that works well for the Moon and early Artemis missions and allow it to evolve so that we can be prepared for Mars when the time comes. Next slide. There's also the notion, the important, I think, transition between doing sortie missions at first and at some point establishing the Artemis base camp, from which point you're essentially in fixed base mode, and that's when the operations will have to be conducted very differently. Next slide. So, in conclusion, Artemis ops are an opportunity to make the autonomy leap to Mars. The Artemis base camp will help prepare Mars fixed-based operations. The crew's tactical autonomy on the Moon and Mars might be aided by artificial intelligence down the road. And the Haughton-Mars project and other sites are relevant and versatile test beds for Moon and Mars science ops concepts. Thank you.
Thank you very much, and well done on the timing.